The accuracy of visual odometry largely depends on the quality of the images that are being fed to the algorithm. So selecting the right exposure parameters for the camera is crucial for VO's success. For instance, motion blur reduces VO's ability to successfully detect and locate features. Noise generates many false feature matches, which can throw VO off. Finally, high dynamic range scenes also lead to under or overexposed regions where no features can be detected. To limit these detrimental effects, auto-exposure algorithms are meant to select exposure parameters that are optimal with respect to some metric. For instance, most camera built-in auto-exposure use PD control to minimize the difference between the average image intensity and some reference value. However, the camera's built-in auto-exposure algorithm is not specifically targeted towards producing optimal images for visual odometry. Instead, other auto-exposure methods associate a metric to each incoming image. These metrics are proxies of VO accuracy. One general approach is to reactively adjust these parameters. Reactive methods are fast to compute, but require exploring the parameter space, leading to large exposure variations. To avoid sampling the parameter space, predictive methods incorporate some learned or known model of the camera. However, no existing method fully exploits the camera photometric response function or directly considers the effects of motion blur and noise. The present approach follows a structure similar to that proposed by Shim in 2018. Each new frame undergoes a set of discrete transformations that simulate different exposure values. Unlike Shim's approach, the one proposed uses the camera PRF to make more accurate simulations. One limitation of this approach is that the future intensity of saturated pixels cannot accurately be predicted by the PRF. Hence, a feedback mechanism is also incorporated into the method that compensates for saturation. Finally, gain and exposure time are dynamically adjusted based on the average optical flow. When the camera motions are large, the exposure time is kept low in order to minimize motion blur. For small camera motion, gain is kept low instead to minimize noise. For validation purposes, the proposed algorithm is benchmarked on a motorized motion table capable of in-plane translation and yaw rotations. The motion table allows to repeat the same camera trajectory with different auto-exposure algorithms. All recordings are post-processed with stereo or SLAM. Under static light conditions, the proposed algorithm selects the exposure parameters that are close to the best hand-tuned static parameters. In comparison, the camera built-in auto-exposure and Shim's method tend to select images with lower exposures. The suboptimal exposure of the camera leads to a deterioration in VO performance when using the camera's built-in auto algorithm or Shim's. Static parameters are, however, not robust to strong light variations. Despite behaving in visually similar ways, the auto-exposure method can actually have a significant impact on VO accuracy. Indeed, results show that the proposed auto-exposure algorithm can cope with varying light conditions better than the camera's built-in and Shim's auto-exposure. Static parameters tuned indoors cannot deal with direct sunlight. Shim's algorithm selects darker frames, and in this instance, it leads to a failed tracking. Without saturation feedback, the proposed algorithm is too slow to adjust exposure parameters after looking out the window. For more details on the method, please check out the paper. The source code is also available on GitHub. Thank you for listening.